In this video, we are going to have corollary to transitivity theorem for finite extension field and just an introduction to the collection of all polynomials, which is denoted as f square bracket x. Now, in the previous theorem, what we had was if L is a finite extension of K and K is a finite extension of F, then L is a finite extension of F. This was given L over K finite, K over F finite, and we proved that L over F is finite. But what is given here in the corollary? This is corollary to the theorem. If L is a finite extension of F, so what is given to us? L is a finite extension of F, and K is a subfield of L. Only this much that we are given. K is subfield of L. Of course, it contains F. So only this is given. L is finite extension of F. Only this much is given. Now, if we have to make use of the previous theorem, then we must have this and as well as this to be finite extension. L finite extension of K, K finite extension of F. Now, if this is the case, then establishing that degree of K over F divides degree of L over F is simple. Because we can, once this is true, the theorem can be used. Once theorem is used, automatically the next step will come, and that will end the proof of the corollary. So what is given to us is degree of L over F is finite. We shall take it as, say, some number n. So once it is finite, it can have basis elements. So we shall take the basis elements as v1 etc. vn. Now, dimension of L over F is finite means K being a subspace. See, you have L, you have K, and then inside only you have F. If L over F is finite means K being a subfield of L, it's a subspace. So if the superspace is finite dimensional, subspace is also finite dimensional over the same field. So K is a finite dimensional vector space over F, which means degree of K over F is finite. So these two we need, of which this we have got. Why? Because L is finite dimensional over F. K being a subfield of L, K is finite dimensional over F. So degree of K over F is finite, we have got. Now we need to have degree of L over K to be finite. So for that we shall consider an arbitrary element, say x in L. Then this x can be uniquely written as the linear combination of this basis element. So these scalars are to be taken only from F. Now the same equation now can be interpreted as x is a linear combination of v1 etc. vn over K, because your you have your alpha i's in F, but F is contained in K. So now that you can call that it is a linear combination of vectors over K. So that means L over K is now finite. You consider x to be an arbitrary element in L, and that is written as the linear combination of the basis elements with the scalars taken from K. So you have degree of L over K to be finite. So degree of L over K finite, and degree of K over F is finite, and also F is contained in K, contained in L. Hence by the transitivity theorem, we must have degree of L over F to be L over K and K over F. We can also, this is called tower diagram, F, K, L. So degree of L over F is finite given. We proved that K being subspace of L, it should be finite dimensional. So degree of K over F finite we had, and any x in L being written as the linear combination of the basis elements over F is same as writing that over K also, which means degree of L over K is also finite. And we are given that this to be finite. So degree of L over F is degree of L over F is L over K into K over F. So from this is some integer. So whenever you have A is integer times B, then B must divide A. So using that, you have degree of K over F dividing degree of L over F. So this is the corollary to that transitivity theorem. And we will have, see, in what follows, we need to know about the polynomial space, which you would have already come across in BSc itself under linear algebra. Vector space, one of the examples. So there you would have had fx, collection of all polynomials, and only in this semester that in some of the syllabuses you will have in some university or college, they have and this fx, which is collection of all polynomials over f, to be the properties of them will be studied in that section. In Herstein, it is given in 3.9 polynomial rings. So the entire section is devoted to fx. Entire section is devoted to fx. Fx is collection of all polynomials over f. So you can simply write like this, and these alpha is range over f. Over f means the coefficients are taken from f, and n is non-negative integer. Now, what you will be establishing in 3.9, if it's in your syllabus, then you'll be proving them in that section that fx under addition and multiplication of polynomials is a commutative ring, and not only that, it is a Euclidean ring. Whenever you have Euclidean ring, you need to talk about the d function. The d function is d of any element is nothing but degree of that f of x. So as for polynomials are concerned, two simple things you must remember. One is it is over what? Which field? Which means the scalars are from which field? That is to be noted. Polynomial over f, that wording should be there. Over what? Which field? So polynomials over f. So these wordings are to be understood well. And another aspect of polynomials is about its roots. The roots of given polynomial. So roots and it's a polynomial over which field. So they play a major role in the rest of the sections. And in polynomials, another word that will be used quite often is irreducible polynomial. Now, when do you say that a polynomial to be reducible? When do you say that it is irreducible? And irreducible over what? So here that over means you must have the roots in that particular field. See, when we consider this x square plus 4, it's a polynomial over q. It's a polynomial over q. It's a polynomial over q. Because over means what? And the coefficients should be taken from that. Right. Now, how about the roots of this polynomial? When you solve for x square plus 4 equal to 0, you have your x to be plus or minus 2i. You don't have I in q. So, you don't have roots of this polynomial in q. If you have, instead of this x square minus 4, then its roots are plus or minus 2. So they are the roots available in Q. So that means x square minus 4 is reducible over Q, whereas x square plus 4 is irreducible over Q. In the same way, if you consider x square minus 2, say, then its roots are plus or minus root 2. So it's a polynomial over Q. Over Q means the coefficients are to be taken from that Q. Roots. Then the roots of this polynomial are not in Q, and therefore they are irreducible polynomials. So given any polynomials, What two things that we must know is it's a polynomial over which field, and what are the roots? Do they lie in F itself, or they do not? I mean, the polynomials do not have roots in F. These two categories. If they do not have roots in F, then you call the polynomial to be irreducible. Otherwise, it is reducible. Now, there are results which have been established in section 3.7 Euclidean rings. Those results are again true for elements in Fx also. Fx is a Euclidean ring, so all those results that have been mentioned in section 3.7 hold good in the case of Fx also. So these are there are a lot of results, but these are the main results that will be used quite often. One is GCD, the other one is LCM. This you would have come across in the previous semester in rational canonical form, or even in Jordan form. So all those, especially in rational canonical form, you would have made use of them. It comes in Jordan also. So whenever you talk about the characteristic polynomial will play a role. So whether you are using GCD or LCM there, that's different. But polynomial play a role over there. So next concept is relatively prime. Whenever f of x and g of x are relatively prime, that is, they do not have common factors other than 1, then in that case we write it in this way, and a result which states that the same thing can be written as, you can find two more polynomials, say r of x and s of x, such that r of x into f of x plus s of x into g of x is 1. This one is constant polynomial. And then another result is every ideal is a principal ideal. Every ideal is a principal ideal. And what is the meaning of it? Any ideal in Euclidean ring is a principal ideal, and that is how, after proving that that in any integral domain with unit element in which all the ideals are principal ideal, you have that ring itself to be called as principal ideal ring, and every Euclidean ring is a principal ideal ring. That you would have come across in section 3.7. So every ideal is a principal ideal, which means when I consider, see in fx itself, suppose I consider V to be an ideal. This ideal should be generated by a polynomial. This polynomial will generate all the elements in capital V. Then this is true. Why? Because it is present in our fx. Fx is a Euclidean ring, so every ideal in a Euclidean ring is a principal ideal. Every ideal is a principal ideal. So this result is very important, and in the same way, whenever m is generated by p of x, where p of x is irreducible, then you will have m to be maximal. An ideal is said to be maximal. Definition is different. This is criterion. So an ideal m is maximal if and only if it is generated by p of x, because it's a Euclidean ring. It has to be like this only. And what is the condition to be imposed on p of x is it should be irreducible. Whenever you have p of x to be irreducible, then automatically the ideal generated by that irreducible polynomial will be maximal. It will be maximal. So on this GCD and LCM, they are similar to your, in the case of integers, what you have mentioned, or even in Euclidean ring you would have mentioned. So the same thing with the polynomials you can have. So, so in this video we had the corollary to the transitivity theorem, and then just an introduction to this collection of polynomials over F. So in the next video we can talk about the field adjunction. What do we mean by or what is how do you perform the process, namely adjoining your A, an element which is not in F, which is not in the base field F, And by what is the meaning of saying that you adjoin an element A to F of A? So field adjunction, the process is called field adjunction. So all that will be dealt in the following videos. Thank you.